Okay, we just give you some idea about the flow structure of the free jet, and try to give you the idea to identify the location for a given diffusion frame or a premise frame with a given mixture ratio, and the frame pictures show you there's some a possibility for a given fluctuating flickering diffusion frame has a longer frame length, or you may have a small premise frame accompanied with the outer diffusion frame. That means the double frame structures. Now you can see there is a tremendous big difference between a single diffusion frame and for a single premise frame. For a single premise frame, they are small and show you the blue color appearance, and they have a more stable frame characteristics. You can see for a jet flow. Now we try to look at more detail from the experimental observation. Let's turn your, 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 your notes about that is the combustion sites, page 1.4. And here we start to learn the flow structure from the experimental observation. This is the typical temperature distributions for a given premise frame. Here, this experiment basically show you the temperature distribution for a frame with the 8.7 natural gas. In the experiments, when they say the natural gas, usually the composition for natural gas is mostly contains methane. You can think about 8.7% means the 8.7% methane concentration in the air, which means the condition is lean, right? The stoichiometric ratio for methane premise frame is around 9.5%. Now you have a 8.7%, okay, and they just show you the given condition on your experiment with the flow velocity, the boiling flow rate of the natural gas is around 224 cc per second, and they use the rectangular burning the burner tube, and this is the cross section area, and they show you they do the measurement on the temperature, and this is a typical temperature distribution for the flow structures, basically for a given 8.7 natural gas premise frame. Okay, you can see starting from here, closer to the exit plane or burner, you can see there is the nicely have a so-called, there's the abbreviation for the region. They say luminous zone. Usually, luminous zone use this term used to describe the location of your frame. But people you should know that luminosity basically coming from the earlier stage. They tell you the luminous. Luminous means that there is bright, right? There's bright. In ancient years, people use the wick or use the candle to light it on. That means when they say luminosity means that they see the yellow color. Okay, it's better to give another name. Basically, we use the so-called visible zone instead of the luminous zone. Luminous zone usually to identify the location of diffusion frame, because the diffusion frame has the yellow color, and the identification on yellow color is better to be use the luminosity to represent it. But for the blue premise frame, it is better to say this zone is a visible zone. Okay, then you can see this is a blue frame. The location of blue frame nicely is a cone frame, and you will find out the temperature still increase. There is the iso temperature line. Okay, you can see after that means the in the downstream or luminous zones, the temperature still increase. Very close to the luminous zone, the temperature is around 1600, right? Now they increase to 1700, 1750, and 1800, continual increase. But people, from one-dimensional premise frame description, we understand luminous zone or visible zone actually is ahead of the highest flame zone, highest flame temperature, right? Because the luminous zone represents there is a large amount of intermediate species. They need to be complete their recombination to the water and carbon dioxide later, which means the the maximum temperature will achieve when they passing through the visible zones, then they will reach to the maximum temperature. The location of maximum temperature should be a little bit farther compared with the location of luminous zone. This is true from the one-dimensional flow identification, and you can see there is a similar way, but you can see there is some kinds of there's a big difference compared with the temperature difference compared with the temperature at the luminous zone and in the downstream. There is another effect you can see. This is this show you the for example, I give you the 100 the 1800 nights. Okay, this is 1800 degrees Celsius night. They follow by this way. Why you can have this isothermal night? Because when you have a burning in this region, which means that this is a high temperature region, then they will give you the idea about the density is pretty much small compared with the that in the surrounding, because in the surrounding the temperature is around, maybe we can say is around atmosphere temperature is 20 Celsius. In this sense, there is a big difference between the density. We have a larger density in the outer region, small density in the burning region. Now this will produce a so-called density difference. Then we will have a so-called natural convection, or we call it buoyancy effect. This buoyancy effect will push your hot products to move to the downstream. That means that you can have the very stiff boundary to show you in the outer region temperature is low, but inside of your hot temperature region, they were more concentrated in this area. And this kind of pushing by the gravitating force, the buoyancy effect, will push your high temperature products more concentrated in the downstream side here. Okay, and you can see the high temperature, the highest temperature occur around here, 1863, right? 1860 around here. And this we can imagine this will be the location of the maximum temperature, or we call adiabatic different temperature. But in this case, it is not an adiabatic different temperature, because you should have some heat loss by radiation or by different kinds of heat transfer to the outer region. But anyway, here they will reach to the maximum flame temperature. Later on, the temperature will decrease. Okay, if you look at the temperature distribution along the axial directions, you can see the temperature starting from the tip of your luminous zones. There is around 1600, then 1700, 1750, 1800, 1830, continue increase to around 1863. Then they start to reduce, decrease, and continuously in the downstream region along the axial direction. Okay, if you look at the temperature distribution along the axial direction, you can see the temperature will reach to the maximum temperature, then they reduce because there is some heat released from in the downstream side by different kinds of heat transfer mechanism to show you the temperature variation in the downstream high temperature zone. Okay, this is a typical temperature distributions for a given premixed flame, especially for the limb premixed flame case. In this case, there is an influence coming from the buoyancy to push your hot product to move to the downstream. Therefore, you will have a very sharp boundary near in the flow to tell you there is a gradient, very sharp gradient, to tell you the pushing or your natural the natural convection to push your hot flow to move to the downstream. this is a temperature measurement, but many people use different kinds of experimental techniques to show you where is the location of your premixed frame, and you need to know the concept of different experimental techniques because they use different technology to determine the location of premixed frame, but you need to careful to identify the differences on the experimental results. In this part, we already give you the summary on the results. You may use different kinds of method. I list several methods you may have. The first one, you can see the top one. There is a cone, right? And there is a cone. We call this as a luminous zone, or we call visible zone, right? I mentioned most people use luminous zone to represent yellow color frame. But in reality, for premixed frame, usually because we do have a few premix with oxygen, they do not have a strong possibility to produce the yellow color, to produce a carbon particle. Then sometimes we call this a visible cone instead of the luminous cone. But if you burn the hydrocarbon fuel with the high concentration of carbon, then it's still possible to have a yellow flame. Then this luminous zone is suitable to describe it. But anyway, this zone means that you can observe it, okay, either by yellow color or by blue color, okay. In the upstream side, then you can follow up by this is a reaction zone. And the more when you closer to the upstream side, then this is a cone determined by shielding techniques. And the nearest the cone actually is observed by shallow graph cone. By different kinds of experimental techniques, they will give you some image pictures, but they show the different locations for the positions you need to identify. Let me show you why they have these kinds of discrepancies between different the results from the different experimental techniques. In general, I think this is the homework for you to find out what's going on about the so-called shadow graph and the shielding photography. These two technical methods you need to try to find it out, and you will see how to do the experiment by using these kinds of techniques. In general, shadow graph. Maybe I should say the shielding photograph first. The shielding photographs by using some optical techniques, then they will show you the image of a given premixed frame. Usually they reflect the density gradient, the first derivative with respect to the density of your flow, or you can convert to the temperature gradient because for premixed frame, they are gaseous mixtures, right? Then based on ideal gas law, the density variation were compatible with the temperature variation. They are proportional. That means that if you can measure the density gradient, that means that point show you the same temperature has a gradient. Now, the shielding photographs will give you the largest value for density gradient or temperature gradient. Where is that? Later on, I try to give you some review on our one-dimensional premixed frame structure. Then you will see where is the point. Then you need to find out shielding photograph will show you the largest values for the temperature gradient and the temperature or temperature density gradient or temperature gradient. Then they were more closer to the position is more closer to the ignition temperature. Okay, I want to mention this is the first point. The next point, when you go through the experimental techniques on shadow graph, actually they measure the derivative or the density gradient, which means the second derivative of the density or second derivative with respect T. temperature. Okay, then they will show you the earlier inflection point of your temperature profile. Then the location for your cone, the cone image determined by shadow graph will occurs in more upstream region. Okay, you will first reach. You can see this is the position measured by the shadow graph. Then the positions for the cone measured by the Schleiden. Then you go to the reaction zone, and then you go to the luminous zone, visible zone. Finally, you can have the flame temperature, highest flame temperature very close to this line. Okay, then let's go back to see our one-dimensional flow structures for premixed flame. Then you can figure out how to think about those differences with different locations. Let me change the lecture materials a little bit. Wait me a second here. We need to go back here. Okay. Okay, you can see here very clearly, right? Actually, those kinds of experiment techniques depend on the temperature variation. Even you do the measurement based on the density differences based on ideal gas law. You can look at the density variation by converting the temperature variation. Okay, then you can see when you go from the very far upstream, the temperature do not have any change. Then you cannot see any image for your cone. When you're approaching to the precision zone here, actually this tell you the temperature increase very fast. They have a so-called the largest value on the second derivative of the temperature. Here, this is show you when you have an image at this point, that means that they will be taken by using the shadow graph. Okay. Then you move, you can see the temperature gradient that will reach to a maximum value very close to the ignition point here, right? Therefore, when you have an image at this location, that means that they can be taken by the shielding techniques. Then they will, when you move further to the downstream side, then you can go to the visible flame zone or reaction zone. Later on, you will reach to the highest temperature zone here. Okay, this is a consequent positions for measure or image by different kinds of experimental techniques. Now we go back to the slides. Now you can understand there is the differences between the image measured by different techniques. The earliest you can find is by shadow graph, then shielding, then reaction zone, then luminous zone, or we call it the visible zone. Okay, that means that you need to be very careful to identify the real location of your given premixed frame by using different kinds of techniques. Basically, from a theoretical analysis and our experimental observation, we find out the frame thickness of a given premixed frame. The frame thickness usually represents the reaction zone because there is a lot of intermediate species. They are ready to react or recombine to become carbon dioxide and water. And from the theoretical analysis, we understand the frame thickness Lc is a proportion to the pressure of minus n divided by 2 power. N is the reaction order. Actually, we already explained to you the reaction order need to be determined by experiments because those N, for a given chemical reaction, you cannot have just a single chemical reaction to complete or to represent the overall multi-step chemical reaction. When you combine it, and we say this is one single chemical reaction mechanism, then you need to do experiment determine because the chemical reaction rate is proportion to the, for example, you use the fuel and the oxygen, right? Then you need to use the fuel to the power of the number of reaction order for fuel and times the oxygen concentration to the power of the oxygen reaction order. And these two reaction order need to be determined by experiment. But usually, people think about for a given chemical reaction rate or a given chemical reaction occurs, they need to have a two molecule react together, right? And in many simple mechanism, we believe you can use one molecule, few molecule react with one oxygen molecule. That means the reaction order is 1:1, and then N is the total reaction order for the fuel and oxygen, N equal to 2. Okay. N equal to 2 here, when you have an N equal to 2, then that means that they tell you your flame thickness is inverse proportion to the pressure. Okay. If you have a lower pressure, the flame thickness will be enlarged. Okay. And this is the first one I want to mention. In general experiment, especially for laminar flame in our laboratory, we find out the flame thickness for a given premixed flame is around 1 millimeter only. 1 millimeter is quite thin, right? 1 millimeter means all the chemical reaction will complete at this narrow positions to complete it, which means that you can see the chemical reaction rate are very fast. Okay, they complete all the multi-step chemical reaction, then they produce the so-called products. When you find out there is the inverse proportion, the flame thickness is inverse proportion to the pressure, and people will think about it. When you do the experiment, you just realize the flame thickness is only 1 millimeter, right? Then you try to figure out, can we measure or do some investigation on the flow structures inside of the flame zone, in your flame thickness in the flame zone. Since the flame thickness is quite small, then all the for example, you want to insert the thermocouple, you cannot have too many point for your measurement, right? Because the thickness is flame zone is quite thin, and the thermocouple is it's thin but not thin enough to make so many position to measure. That means that when you try to look at more detailed flame structures, especially in the flame zone, there is some technique. There is the idea to tell you can try to do the experiment under low pressure. Okay, when you have a low pressure condition, then your flame thickness will be increased. Then you can have more point to be measured to be insert temperature, thermocouple, or maybe the suction tube, because you want to do the concentration measurement. Then when you enlarge these zones, then you can have more points to do to insert your experimental instrumentation into the flame zone. And here they tell you the other important characteristics. Here they tell you this flame thickness is proportion to the square root of lambda divided by Cp. Lambda divided by Cp, as you remember, this is a so-called thermal diffusibility. And I will tell you this is a very important dependence to be compared with those kinds of dependence on dependence described in diffusion flame. Here they tell you this is a square root. Okay. And then the other one, you can see this flame thickness is proportion to the exponential function. I'm sorry, here there is the minus sign. Here I think I forgot to put it. There's a minus sign, and that depends on the activation energy, the comparison between activation energy and the flame temperature. And I already mentioned activation energy is a large value compared with the thermal energy. And if you have a minus sign, minus large value, then exponential function of this minus large sign, large value, that means they were equivalent to a small value. Okay, and this contribution from the exponential function will give you the idea on the value of your flame thickness should be very small. Okay. Now we go to there is another thickness need to be compared with the flame. We call this Puritan thickness. polyethylene thickness, basically the thickness of your polyethylene zone means the temperature increase point up to the flame temperature zone, okay, or ignition temperature. This zone, the thickness of this polyethylene zone is larger than that for the flame thickness. And they have some comparison. Usually people will use this this relation. If you use the flame thickness divided by the polyethylene zone thickness, there's one order reductions. With the order that depends on the definition from the theory, this epsilon is equal to R naught TF divided by activation energy. Actually, the upper parts represent the thermal energy you will have, right? And activation energy in the lower part to have some comparison. Usually for the hydrocarbon fuel, the activation energy is around 40 kilocal per mole. There is O here, it's disappear. And when you substitute those data into these equations, then you will find out epsilon is approximately equal to 0.1, which means when you have a 1 millimeter thickness of flame thickness, then your polyethylene zone is around 1 centimeter. Actually, this is true for our experimental observations. 1 centimeter polyethylene zone, then you have a 1 millimeter flame thickness. Okay. Additionally, I need to explain again. If you look at the flame thickness, you will find out this the expression tell you. For example, for the P, as I mentioned, when you look at the pressure for a given gaseous mixture, the P represents the collision rate per unit volume. Okay. Now, if you have a lower pressure, means the collision rate will be reduced. When you have a reduced collision rate, the chemical reaction rate is reduced too, because based on the Arrhenius law. Which, therefore, when you have a lower pressure, I just mentioned, then the flame thickness will increase. That means they need to have a larger region to complete chemical reaction because the collision rate of molecules is less. And here, lambda divided by Cp represents thermal diffusibility. Thermal diffusibility come from for the flame temperature, for temperature profile of your premixed flame. You can see we have a concentrations, the fuel and the oxygen moving from the upstreams, and they will have a big drop to the zero or have a certain value in the downstream side. This gradient tell you the concentration gradient, right? And you find out the temperature initially is small, but they will increase to the higher flame temperature. You can see there is the temperature gradient. When you see the gradient, now you figure out that the diffusion transfer become very important for the premixed flame. The mass will diffuse into your flame, and the flame will diffuse your thermal energy to the upstream sides. And those diffusion transfer for the mass and for the thermal need to be compared. Usually, we find out they are almost equal, and we call this as a so-called Lewis number, and they approximately equal to 1. But sometimes they are bigger than 1 or smaller than 1. They will give you different kinds of outcomes, and we will discuss as the unbalanced diffusion process, and we try to think about the physical meaning. Now, the second term represents basically the diffusion transport influence coming from diffusion transport. The final, they basically is controlled by the so-called the activation energy, the Arrhenius law. Okay. Now we go back to we continue to look at the temperature. Actually, we already explained it. Flame temperature is a very good indication to introduce the burning strength of a given premixed flame. Usually, if you have a burning in the pure oxygens, the highest flame temperature occur at the stoichiometric ratio. But you burn your fuel with the air, then the maximum flame temperature will move locate at a slightly rich condition. Those kinds of observation is usually confirmed from the so many experimental results. And this is a typical plot I give you. if you change the fuel stoichiometry, and here they tell you phi equal to 1 is under stoichiometry ratio, and the right hand side, if phi larger than 1, that means that you are under rich condition. The left hand side, if you equilibrium ratio smaller than 1, then this will be the lean condition. For example, here, if you look at the carbon monoxide burned with oxygen, you can find out the maximal value occurs at phi equal to 1. Now, if you change to burn the carbon monoxide with air, then the maximal value will shift a little bit to the rich fuel side. Okay, I think we already explained this very earlier when you use the simple chemical thermodynamics relation. I already emphasized. And here there is some typical flame temperature I want to show you in different kinds of conditions with different fuel. Here you can see ethylene for air and oxygen under 1 atmosphere pressures. They have tremendously different temperature, right? For the pure oxygen, they can flame temperature with reach to the 3410 K, and for the air case, the temperature is lower usually because for the air case, because in the air we have a nitrogen will absorb certain amount of heat, then overall flame temperature will be reduced in compared with the pure oxygen cases for different kinds of fuel. Okay, you can see, yeah, for heptane, for hydrogen, okay, so 30 and 80 larger than 24 for the case of oxygen case, comparing with air case. Methane has a similar way, but most important thing I want to mention from this table, the pressure influences. You can see here for the methane burning in the air, you change the pressure from 1 to 20, you can see the flame temperature is just increased by 60 K. It's very small. And for the pure oxygens, the increase is a little bit higher, around 400, maybe less than 400. That means that there is less than 10% increase. Okay, which means the pressure has a certain degree of important consideration to in the burning process, especially for the flame temperature, but it is not too much, especially for if the influence coming from the air. The nitrogen in the air, the influence of nitrogen is more important compared with the influence from the pressure. The other one I want to mention again here, they mention from this table, they mention from the experiment, they find out the maximum flame temperature for the air burning for the ethylene burning in the air, they reach to 2600, right, at 1.3. That means a slightly rich condition. Okay, but surprisingly, for our understanding, for burning ethylene in the pure oxygen, this show occurs at a stoichiometry ratio equal to 1, right? But here in this case, you can see they reach to the 3410 at the equilibrium ratio equal to 1.7. There is another reason because the compositions of ethylene in the very rich regions, they will show you less heat absorbed, and the compensation between the oxygen absorptions heat, they do this kinds of effect. I do not have a time to give you the detailed description, but these differences, usually I just mentioned the maximum temperature occurs at the condition or at the stoichiometry ratio, right? But here is under a very rich condition, and those due to the decomposition, thermal pyrolysis of ethylene, the heat absorbed by ethylene and oxygen, they need to balance, and the best one. The best condition is under 1.7, then they can reach to the maximum flame temperature here. But anyway, this table just try to confirm the results in this table, and you need to remember for most of the hydrocarbon fuel, burn in the air, they will reach to the maximal temperature in a slightly rich condition. And from this figure, additional phenomena I need to mention here. You can see for different kinds of burning conditions, then they will have some limitation for the plot. For example, this curve will stop at this point in the lean side and start this point in the rich side. That means that you have a so-called lean limit and a rich limit. When your mixing ratio exceeds a lean limit, which means smaller than the limit or larger than the rich limit, you may not have the flame exist. That means that you cannot ignite it. For the reason is quite simple. For the lean case, if you have a too lean, that means the fuel is not too starch enough. If you do not have enough fuel, that means that you cannot have enough heat of combustion be released in the chemical reaction mechanism. But for the rich condition, that means that you do not have enough oxygen to participate to recombine those kind intermediate structure to carbon dioxide and hydrogen and water. That means that you still cannot deliver enough heat of combustion to continue burning. That means that under this the limitation of this lean and rich limits, then you will not have a flame exist. Then we call this the so-called inflamed limited limits. Some people will say flame limited limit. For example, for the methane, the lean limit is 5.5%. Upper limit, rich limit is 50%. We call this as a two boundary for you can choose if the concentration just inside of this boundary, this extent, then you can have a so-called you can have a flame. Out of this this boundary, then you may not have a flame. I said may not means some concentration. If you have a mixing ratio is under the lean limit or rich limit, you can still have some additional support. For example, for premixed, the concentration is around mixing ratio is around 4%. But if you have an outer heat source to support them, that means that you have a super adiabatic. You have some heat support, then maybe this flame can exist. The typical observation you can find out in our previous experiment that tell you that when you reduce your methane concentration from 100% to 20%, you will find out there is the double flame, right? The double inside of your jet, there is the so-called rich premixed flame. Now this is 20%. 20% is about is higher than 50%. Definitely from our observation of our experiments results or definition here, you should not have a flame, right? But in our previous experiment, actually there is additionally support from the outer diffusion flame. That means that you have a double flame. Originally, if you put the so-called 20% rich premixed flame in an environment without oxygen, that means that you just try to inject it out in a nitrogen environment, and you just can have a rich. Can you have a rich premixed flame with the concentration 20%? It is impossible. But for the oxygen environment, there is the outer diffusion flame. This diffusion flame has some burning intensity to support the burning of a rich premixed flame. That means that you can have the rich premixed flame under concentration higher than rich limit because of the diffusion flame support. But this table actually tell you there is the purely premixed flame without any support, then they will have some limitation. The burning will be restricted by the lower and the upper limit. Okay. And this plot tell you from the experiments, they tell you from the limits, they do not have too much variation when you change the pressure. This here, for example, there is atmospheric pressure. You can see there is a lean boundary, and this is a rich boundary. Now, when you try to reduce the pressure, you can see the boundary do not change. Okay, the flammable area still restricted by the D limit and the reach limit. But when you reduce the pressure to a very low value, okay, then you will see there is a inflammable region occurs, because when you reduce the pressure to this this extreme range, the collision rate of molecule become very small. The Arrhenius law tell you there is almost no enough collision rate to give you the enough value, enough amount of to enhance the chemical reaction rate. But in general, you can see the pressure do not give us a strong influence to the D limit and the reach limit, which means from the limit basically controlled by the chemical mechanism. Okay, if you do not have enough oxygen concentration or you do not have enough fuel concentrations, they cannot provide a suitable amount of heat of combustion to continuous the premixed burning.